And let's wait a couple of minutes before we start today's lecture. All right, let's start. Good morning again, everyone. Today, what I'm going to do is I'm going to finish the geometric preliminaries that we have discussed last time. I'm going to talk about line representation and intersection of lines with circles, how to get a circle that passed through 3 points, and line and circle equations. I'm also going to talk about the parametric line equations. So as usual, if you have any questions, you can type in the chat. Oh, you don't hear my voice? Okay, let me check again. The microphone seems to be working. So does any of you can hear me? Oh, okay. A couple of you cannot hear my voice. Let me check again. I will check my microphone. Test, so this one seems to be working. I'm unmuted. Yeah, my mic is on. Test. I can switch back to this one. Let's try. All right. Can you hear me now? Let me see the chat window again. Okay. So you can hear me now. I'm using the webcam's mic. Somehow this microphone it didn't work. It worked yesterday, but anyway. So okay, so I'm going to be using the webcam's microphone. So I'm going to start sharing my screen again. Now everybody can hear me. All right. So let me get the chat window on shown again and the participants. All right. Okay. So today, as I said, the plan is I'm going to finish the geometric preliminaries that I started last week. And then Yeah, by the way, I'm not using this microphone. I had another microphone that I was trying to use, which worked yesterday, but today somehow it didn't work. But the good thing is I have three options in terms of microphone. The webcam also has a microphone, so now I will be using that one as input. All right, so I'm going to finish the geometric preliminaries, and then we are going to start our first geometric problem of convex hulls. And the reason that we are going to discuss convex hulls is also to tell you about the style of the book, what we are going to discuss in terms of a geometric problem, not observation of geometric properties only, and the algorithmic and data structure related material that we need to solve these problems. So this is convex hulls will be an example problem that the book uses to show what kind of problems we will discuss in the book, how we are going to analyze these problems, and how we are going to provide algorithms. It's going to be an introduction to the pseudocode used in the algorithm, and you are going to understand at what level we will be discussing these problems. All right, then I'm going to start chapter 2, which is line segment intersection, and we are going to. Oh, by the way, I should turn this on again. It's actually on because OBS Studio is actually recording using this microphone, so I shouldn't take it off. Actually, it's still on. All right, let me check OBS Studio again. Yeah, it's taking my voice correctly. All right, so and we are going to start our first computational geometry specific algorithm style, which is the plane sweep technique. So we are going to be talking about this plane sweep technique, and I'm going to be using a simpler problem first, the closest pair problem to demonstrate the plane sweep algorithm, its elements. And then in chapter 2, we are going to be using the same algorithmic technique, the plane sweep technique, to solve the line segment intersection problem. So the line segment intersection problem, we are going to start talking about it. I'm going to describe you the basic algorithms outline. We will go over the pseudocode quickly, but the analysis of the line segment intersection algorithm, I'm going to leave it for next week. So just like I want to be in parallel with section 2. So in section 2, yesterday night, what we did was we just came until the end of the pseudocode of line segment intersection. And the plan is I'm going to first have a 50 minutes of lecture. We'll have 15 minutes break. Then we will have like 1 hour and 15 minutes of lecture, 2 hours, a little bit more than 2 hours in total. And we are going to finish early around 12. All right, so that's the plan. So let's get back to geometric preliminaries. Last time we talked about line segment intersection, how we can use cross product to determine whether a point is on a certain, so given an oriented line segment like this from A to B, we can actually check whether this point P is towards to the right or to the left of this line segment from A to B, or line from A to B. And we use this to check whether a point is inside a convex polygon. We can use it to check the convexity of a polygon, or we can use this, the left-hand side, right-hand side identification, to check whether two line segments intersect. Okay, if two line segments AB and CD intersect, if D and C is on two different sides with respect to the line from A to B, and in addition to that, A and B is on two different sides with respect to the line from C to D or D to C. Okay, it doesn't matter. You can have from A to B or B to A. They will be, as long as these two are on two different sides from the perspective of both of the lines, then the line segments should be intersecting. Another thing that we could do is we could just form the line equations. The parametric line equation we have used was, for example, let's call this line 1. Any point on line 1, let's call them P1. Any point on line 2, let's call these points P2. their equations will be like this. So we have seen to form this equation easily. Actually, so P1 we parameterize with T. This is the parametric line equation. It's simply A plus B minus A T. Okay, so this simple equation is the line equation for line 1 from A to B. And as you can see, A is a vector here, two-dimensional vector is a point, but it's a two-dimensional vector. B minus A is a vector which shows the direction. So start from point A, start from this location, go in the B minus A direction, and do it. And this T is a scalar parameter which changes from minus infinity to plus infinity if you're having this line. But if you're interested in the line segment only, the T is going to be between 0 and 1. Okay, so if T is between 0 and 1, that's the line segment. In order to find the intersecting point, all you can do is, it's very simple, write P2, but here these two parameters T actually are two different variables, because this parameterization, if we use this T to parameterize the points on this line segment from A to B, so we should call them T1 and T2 because they are two different things. All right, P2 simply is going to be, we can start from C, go towards D, so our direction will be D minus C, T2. Okay, so this one is the second parametric equation. So in order to find the intersection point, all we need to do is find a point in which these two P1 and P2 are equal to each other. That's the intersection point. So therefore, we need to equate these two equations. In order to find the intersection point, what we do is this: A plus B minus A T1 is equal to C plus D minus C T2. As you can see, A, B, C, and D, they are known here. They are given to us. We know what A, B, C, D are. They are points, 2D points. And here, the only two unknowns are T1 and T2. So we need to solve this equation to find the two unknowns. Now, isn't this a problem? We have two equations. Actually, I just blurted out the answer. Actually, I was meant to say we have one equation, two unknowns, right? T1 and T2, two unknowns, and there seems to be one equation. How can this have a single unique solution? Any ideas? Two unknowns, there seems to be one equation here. But is it really one equation? You can write in the chat box. Yeah, it's actually two equations, not one equation. Since these are, yeah, actually we have two. That's correct, because these are vectors. So AX plus BX minus AX T1 makes it a single scalar equation. And the AY, the X coordinates and Y coordinates, gives us two separate equations which relate T1 and T2 both. So two equations, two unknowns. We will have a unique answer if they intersect. If we end up with 0 equals 0, for example, cannot find T1 and T2, it may be the case that the lines are parallel to each other. When the line segments are parallel to each other, there won't be any intersection. What about something like this? Okay, we have two line segments that are not intersecting, but their lines are intersecting. Okay, so if we solve this equation, we are going to find T1 and T2. There will be an intersection point, but what will happen is that either T1 or T2 is going to be outside the boundary of 0 and 1. Okay, in order for, you can use this to test line segment intersection too. You can form the line equations, solve for T1 and T2. If both of them are between 0 and 1, they may be something different. For example, T1 may be 0.1, T2 may be 0.8. Okay, when the intersection occurs, then if they're both within the range 0, 1, okay, if they're both within this range, they will be intersecting line segments. Okay, if, for example, in this case, these two line segments, as you can see, if the intersection point is here, if this is parameterized by T2, if this is by T1, T2 is going to be between 0 and 1. It's within the line segment, but the intersection point T1, if this is 1, T1 is equal to 0 here, T1 is equal to 1 here. As you can see, the intersection point T1 is going to be something like 1.8. Okay, which says that the intersection point is outside the boundary of this line segment. So these parametric line equations are very useful to have these intersection tests. We can, for example, check the intersection of circle with a line segment like this. Now I'm going to jump to circles. I'm going to get a new so here in 2D, a circle can be identified by two things: its center, its location of its center, and its radius. So in order to uniquely represent a circle, I mean just make a circle, we need its center, which is the C. Again, the center is actually a two-dimensional point. It's just like a vector. Okay, so it's composed of Cx and Cy. So it's a two-dimensional vector like this, Cx, Cy. And R is a scalar which shows the radius. And the circle equation simply is the set of points that are on the circle here are actually this locus of points in which their distance to the center is all R. Okay, that's how they are. Their commonality. The common thing about these points is that they are all R distance away from this Cx, Cy. So we know how to compute the distance. Given a point P here, the distance from P to C, or we can do this, the length of this vector P minus C. That's also the distance, right? I mean, this is how we denote the length of a vector. So you can say P minus C or C minus P, it doesn't matter. So the length of this vector is going to be equal to R. So this doesn't look like our regular circle equation, but if you do the actually, if you compute the distance like this, what it will give us is that Px minus Cx squared plus Py minus Cy squared. Take the square root of this, it will give you R. If you take the square root of square of both sides, you will get the more popular the equation that we are accustomed to see. This is the circle equation, but it's basically, it comes from this distance vector. So Px minus Cx squared minus Py minus Cy squared should be equal to R squared. Okay, so that's the implicit circle equation. We can also parameterize the circle equation. We can have a parametric circle equation in which we can parameterize by a single parameter. Again, things like if an object or if something can be parameterized by a single variable, it itself actually is a one-dimensional object. For example, the circle. Just think about the universe of this circle. Any point on the circle, they're like on a string like this. Okay, so they live in a one-dimensional world. Although the circle itself is two-dimensional, and we have lines here that are two-dimensional, that live in the two-dimensional space. If you think about entities that live on the line, their world is one-dimensional because a single parameter t is sufficient to address all of the points on any point on this line uniquely. Therefore, their address is just one scalar. The same thing for a circle. We can actually parameterize the circle by the angle alpha that we make with the x-axis. As you change this alpha from 0 to 360 degrees, you will have infinitely many values, real values between 0 and 360. That will be your parameter. Okay, so any point as coordinate actually could be written in terms of alpha by using sine alpha and cosine alpha. We can actually indicate the coordinate of any point here. So that's the parametric circle equation. But with the implicit circle equation, we can determine whether a line intersects with the circle or not simply by plugging in into this point. We can plug in the points parametric equation. I mean the line equation in terms of these points. For example, if I have a line here from A to B, I know that its equation is, I mean, any point on this line is going to be A plus B minus AT. Okay, so this is the any point on this line. PT is going to be following this equation. So what I can do is, in terms of this PX, I can plug in AX BX minus AXT here. And for PY, I can plug in AY plus BY minus AYT here. The only unknown in this single equation, it will be all scalar in a single equation. The only unknown will be T. And T will be, will appear as squared. T squared, it will be, the equation is going to be something like this: AT squared plus BT plus C is equal to 0. So you will have some equation like this. If you plug in this parametric line equation here, what we will get is a quadratic single equation like this, which may have two roots, which will indicate these two intersection points, which may have one root, in which case our line will be tangent to the circle, or it may have no roots, meaning that no real roots, meaning that the line does not intersect with the circle. All right. So parametric line equations, circle equations, we most of the time equate one with another to find these intersections. In the other thing that I want to mention is that this is also, I mean, this was a parametric line equation, but there's also the implicit line equation that we sometimes use. If you think about this equation, look at this: AX plus BY plus C is equal to 0. So this is a linear equation, right? I mean, X, Y, they do not have powers other than 1. So this is a linear relationship between X and Y. And therefore, actually, it's a line equation. And you can actually turn this into an equation that if you are familiar with, y is equal to mx plus b type of equation. Okay, now this, we sometimes write it like this to show it as an implicit line equation. This form of writing equations, line equations, actually is also extendable easily to 3 dimensions. We can have something like this: ax plus by plus cz plus d. Now I have the z coordinates. I'm now living in 3 dimensions. What is this in 3 dimensions? Is this a line in 3 dimensions? Any answers? So this was a line. Yeah, exactly. That's a plane. Correct. So this is the plane equation. So something linear in 2D. A line like this. The reason I mentioned this is because by having, instead of equality gives you the line. What if I make it less than 0? What does this indicate? What kind of an object is this? Ax plus by plus c is less than 0. What kind of an object is this? Any ideas? You can write in the chat box. Exactly, correct. It's an half plane. So it divides the plane into 2 regions, unbounded regions. This is a half plane, and in the book we will be discussing about half planes. So that's why I wanted to mention this. So this is a half plane, which is actually one part of this line. Unbounded gives us a half plane. An intersection of half planes is always a convex region. We are going to come to that in chapter 3 or 4, I guess. And similarly, if we have in 3 dimensions something less than or 0 or greater than 0, it will give us the half space. So when it's strictly less than 0, sometimes it's called an open half plane, in which the boundary is not included in the half plane. Therefore, when the boundary is not part of the half plane. If it's strictly less than 0 like this, it's called an open half plane. If it's less than or equal to 0, in which the boundary is included in the plane, it's called closed half plane. Okay, so another interesting thing about these implicit line and plane equations is that these coefficients directly give me, if I, by using the coefficients of a, b, x, y, and z, and form a vector out of them, this gives me the normal vector to the plane. So if I have a plane like this, for example, if this was the equation of that plane in 3D, the normal vector, which is a vector orthogonal to the plane, can be obtained by taking the coefficients of x, y, z. So the normal vectors, we can get them easily. We are going to talk about them in chapter 3 again. And similarly, if you want to get the normal vector to the line, if you have a line, the normal vector to a line is another line, which is actually, it's a direction actually, another line. It's a direction that shows the orthogonal direction to this line. I think we can obtain it by just again taking a comma b as the normal direction. Okay, so that's circle equations, intersection of circle with parametric lines, implicit line equation. The final thing that I want to discuss in geometric preliminaries, and if when we come to the related chapter, if there are things that I didn't discuss in geometric preliminaries, we can also discuss them when the time comes. But the last thing I want to discuss is the a circle passing through 3 points. So if we have 3 points, a unique circle passed through them, and that circle can be found by actually forming the line segments between these pairs of points and finding their midpoints. This doesn't look like a midpoint. This looks more like a midpoint than this one. So finding the midpoints and forming the two lines that pass through these two midpoints that are orthogonal to this one. Okay, so let's call them L1 and L2. The intersection point of L1 and L2 is the center of your circle that passed through. In other words, this distance is R, this distance is R, this distance is R. Okay, so this is how you can find a circle that passed through 3 points. And there's a unique circle because the way that I describe these things, the line segment and other line segment, their midpoints are unique. The lines that pass through those midpoints that are orthogonal to these midpoints, they are unique, and they have a common intersection point. How for example, is this always possible? For example, I told you that, okay, the intersection of L1 and L2 is the center of the circle. What if L1 and L2 are parallel to each other? When can such a thing happen? No intersection point. I mean, just think about two lines that do not intersect. L1 and L2 do not intersect. When can such a thing happen? Which means that we will not have a circle that passed through 3 points. Any answer in the chat box? Yeah, when they are collinear, exactly. Their center, if you draw the lines, they will be parallel to each other when we have collinear points, because when we have collinear points, we will have we can only have a circle that is of infinite radius. So that's something, that's a singularity. We will not have them. Yeah, and then the circle will be degenerate. Or if also that's also true. I mean, if we are given 3 points, if 2 points are, I mean, we are given 3 points, but the third point is the same as the second point. Again, it's like 2 points. In that case, there will be infinitely many circles that pass through them. Okay, I mean, if we have 2 points, we can have infinitely many circles in which these two are part of the arc. For example, let me draw 2 of them. One circle is something like this. The other circle in which the distance between them may be the double radius. Okay, so we can, if we have 2 points that are infinitely many circles that pass through them, but if we were given 3 distinct points, it's still possible that we don't have a circle if they are collinear. Okay, so yeah, that's all about. I want to talk about the preliminaries. Now I'm going to start talking about the convexal problem, and in general how we approach. So chapter 1 is really nice. It shows in terms of these computational geometric problems how we approach them, what kind of things we need to consider, like degenerate cases are important. Sometimes they can be handled easily, sometimes not. And also when we approach a problem, we need to make certain geometric observations. Without the geometric observations, you may have the best algorithms, data structures in the world, it will not matter. You have to make some geometric observations. So the geometric nature of the problem you cannot avoid most of the time. You have to do some observation. You have to see something that helps you to solve the problem faster. But sometimes the geometric observation itself is not sufficient if you don't know the algorithms and data structures to solve the problem efficiently. So they really need to be used together in order to have a nice algorithmic solution to a computational geometric problem. So the book talks about these issues. The convexal problem is a very well studied problem. It's studied in higher dimensions as well. Also, there are things that we use. I mean, a problem that doesn't look like a convexal problem may be solved with convexals. This is known as the convexal trick in competitive programming. You may have a problem that doesn't look like it's geometric at all, but if you can represent certain things as points or lines, you can actually use the convexal solution. Okay, I mean, you can use convexal algorithm for a set of points. Also, you can, if you have a set of lines, you can still use the convexal trick to find there's some envelope, lower envelope. So it has really many extensions that can be used. But we are going to focus on the simplest case, 2D convexal problem, which is like an introductory hello world problem of computational geometry. So in chapter 1, this problem is used for that purpose, to solve how we approach a geometric problem and the way we develop a solution. The optimal solution that we will develop for this problem is an incremental solution. That's another algorithmic technique, incremental, finding something incrementally. You have a set of points to process. You may have a set of polygons to process, and you construct your solution by looking at those points one at a time, and you form an intermediate solution. And by looking at processing the next point, you develop your solution into, you update your solution if it's necessary. Such algorithmic technique is called incremental, and it's used also a lot in computational geometry problems. So the solution we will develop will be an incremental algorithm to this convexal. But first start, sometimes the incremental algorithm, when you say generally brute force, you're referring to the incremental algorithm, right? Sometimes it may be brute force. The incremental algorithms, we may be doing certainly updating the solution in a brute force manner, but it may also be possible to update the solution in an intelligent manner by using some interesting data structures. So we will do that in the case of plane sweep algorithm. Plane sweep is also an incremental solution, but we update our solution in such a way that we avoid looking at all the brute force cases while we're updating the solution. Okay, so that will be again, by using some data. If you know your data structures well, you can actually avoid that brute force and have a more efficient solution. And in the case of, for example, certain incremental techniques, algorithms, we actually sometimes randomized things may help. I mean, we may do things like brute force, but it turns out that randomly the brute force technique actually does not spend too much time. If we do the probability analysis of these things, we see that it's actually very efficient. Sometimes the incremental algorithm turns out to be an efficient solution, sometimes not if you're not careful about your data structures. And in the case of plain sweep algorithm, we will see how important that a good data structure is in solving and having an efficient solution to the problem. So let's start with the convex hulls. So a subset of the space. So this is the book also has really nice formal definitions of things. Let me zoom in a little bit on this. So if you look at this definition, a subset S of the plane is called convex. So on any subset, which may be actually disconnected. So if we may have, for example, these two shapes here, left on the left and right, they two together may be this subset S. Okay, when I say a subset of the plane S, it doesn't say it's a connected. Okay, this is a subset of the plane S. Okay, but it is called convex if and only if any pair of points PQ that is an element of this subset, if you form the line segment between P and Q, if that line segment is completely contained in S, all the points on PQ is also in S, then that subset is called convex. For example, if these two together form the subset S, they are not a convex. So actually you can very easily prove that any disconnected subset of the plane is not convex, because if you just take one point from here, another point from here, if you connect them, since these two things are disconnected, there will be points on the line segment that contain them that are outside the subset. Now, even a connected, I mean, if these two are two different subsets, S1 and S2, if you look at S1, it's convex. S2, although it's a connected subset, S2 by itself may not be convex, because when you select the point P and another point P and Q here, you connect these two with a line segment. Part of the line segment is outside. So this is a non-convex subset, while this is a convex subset. So in this convex hull problem, the problem is to find the smallest convex subset that includes a set of given points. So we are given a set of points as input, and our goal is to find the smallest convex set. And the general problem doesn't talk about a polygon. Okay, it turns out to be a polygon, but this convex shape, given a set of points like this, it's actually the convex hull is the intersection of all convex sets that include these points. That's the intersection of, that's a very interesting way to define convex hull. It's really more intuitive to just say, find the smallest polygon that contains all of these points on it. Find the smallest closed polygon, which means that the boundary is included. Okay, so the boundary is part of the polygon. It's interior too. If all the points are on the polygon or inside the polygon, then the smallest such polygon is called the convex hull of a point set. And if you think about this thought experiment, when you have an elastic band around these points and you just let it go, it will snap on to the vertices of the point set. So what we will try to do is, if you look at this example, if you're given these 9 points, their convex hull contains 5 of the points. Okay, it's a pentagon, and the problem becomes, given an input set of points, find the polygon that form the vertices of this convex hull. And we want to usually, when we talk about a polygon, we have to give an ordered set of vertices, and the book uses clockwise order in that regard. Okay, so this clockwise order is what the book uses, and sometimes other counterclockwise could be used. So it's just a convention. All right, so we can, and the output, when we are given the output here is P4, P5, P8. It goes like this, starting from P4. We could have started from P2. So with P2, P9, P4, P5, P8 could be the convex hull. Now, before thinking about degenerate cases, okay, for example, one degeneracy may be, what if there are collinear points? For example, when we have P4, another P10 here, and P9, this P10 is not going to be part of the convex hull as is defined, because P10 is going to be no different than P7 here. It's another point that is on the convex hull. So when we are indicating the polygon here, we should not output P10. Okay, we should output P4 and P9 only, because P10 is already included in the convex hull, and you are going to have a minimal definition of your hull. So therefore, P10, indicating P10 here is unnecessary. It's already on the edge. It's just like P7 is inside the polygon. Something that is on the edge of a polygon is also considered contained in the polygon, because it's a closed polygon. The edge is contained. Therefore, P10 is just like P7. So when we're indicating the convex hull, we just need the vertices, the corners of the polygon that are extreme points. I mean, P10 is also an extreme point in this direction too, but if there are points inside the edge like this, they are collinear, we are going to report only the points that are at the ends of this edge. Okay, so handling this degeneracy, we will come to that later. First, think about a case where we don't have any degeneracies. Okay, sometimes in order to avoid degeneracies, a term that is called general position. So in the question, sometimes it's given that the points are given in general position. It means that no 3 points are collinear, or the x coordinates of all the points are unique, different. Also, no 2 points are on the same vertical line. Depending on the problem, the general position may indicate, just ignore the degenerate cases. Okay, so the first thing we need to do is we need to make an observation on this problem, and you can have many different geometric observations here. The book starts with the basic observation that the convex hull polygon is composed of edges, and these edges are formed between pairs of points. And if you look at the convex hull edge, so the observation that is shown is here. If you look at the ordered edge, if you're going in clockwise direction, our edges are going to be ordered. If you look at the edge from P to Q, we can make this observation that all the points actually of all the remaining n-2 points lie to the right hand side of this directed line from P to Q. And this should be true for all convex hull edges. If you look at go in the clockwise direction, all the points lie to the right of that. Okay, so we will come to, this if statement is going to be a lot complicated for the degenerate cases actually, because not all of them lie to the right if we have something on the line, if there is something, but changing the condition just to say that if all the points lie to the right or on the line here, then it's a convex hull edge. If we do that, that's also going to complicate things, because if we have another point R here in the middle, RQ, PR, PQ, there will be 3 edges, all possible combinations, pairs of these 3 points will constitute a convex hull edge, which is, in this here, although we should just report a single edge PQ, we would now have to report PR, RQ as well. All right, so that's the degenerate cases actually will pose a problem to this if statement in this simple base observation. But let's first forget about the degenerate cases. Say, okay, all the points have to lie strictly to the right hand side of the edge for that to be a convex hull edge. So the algorithm is this. because after this observation, we can directly turn it to an algorithm saying that look at all pairs of um, points, form the directed edge from P to Q, which means that we will also be forming an edge from Q to P. But since in Q to P no points lie to the right, it will not be a convexal edge. So the edge from Q to P is not a convexal edge because all the points do not lie to the right. Okay, in order to be a valid edge, all the points have to lie to the right. And the algorithm is this. So this is also an introduction to the pseudocode that the book uses throughout the book, which is the algorithm is named slow convexal because it's really slow. Given a set of the input is stated, and then the output is stated precisely. The output is a list containing the vertices of the convexal of P in clockwise order, and we assign an empty set to this E. So E will be our edge set, which will constitute the edges of the convexal. Now, for all ordered pairs PQ in this Cartesian set P Cartesian product P, so we'll look at all the pairs of points in which P is not equal to Q. We are not looking at PP or QQ. And we execute this. So this do belongs to this for. For this, do these statements. Do. We have a flag, valid is equal to true. And then we have a for loop. For all points R in P, which is not equal to P or Q. So for all the remaining n minus 2 points, if R lies to, so we are checking, we have a for loop here which goes n minus 2 times. Okay, we can break out of this loop actually when we first find that invalidates this. We are checking all the points. If any one of them lies to the left of the directed line from P to Q, then valid becomes false. Otherwise, we add if valid, if there is no point to invalidate the directed edge PQ, then it must be a convexal edge, and then we add it to the set E. So steps 2 to 7 actually find it fills in this set E in all n cube time. There are n square such pairs. For all of them, for each of them, we test n minus 2 other points, and in total, the worst case complexity is n square. And then step 8, we form from this set of E edges. We need to, they are just an unordered set of convexal edges. We need to form the chain of edges in clockwise direction. And in order to do that, we should have an algorithm in step 8 too. So the book talks about in this pseudocode saying that sometimes we have steps. We just indicate with a single steps of the algorithm, which just is like a single step of the algorithm. It may need some coding or some more elaborate algorithm to execute that step. For example, this step 5, how do we figure out that R lies to the left of the directed line from P to Q? Okay, how do we find this? We have just seen our geometric preliminaries. We can use cross product to do that. So this if statement will just be checking the cross product of Q minus P with R minus P and checking its sign. All right. And so this requires some geometric preliminary. And this step 8 requires some kind of an algorithm. You will start with an arbitrary edge. It will have a starting point and an ending point. And with that ending point in your set, find the edge that starts with that ending point. Okay, and then append it to your chain. So if you implement this algorithm in a brute force naive manner, it will take n square time, because for each of the edges you will be looking for another edge among remaining edges that has the ending point as the starting point. So you may have an n square algorithm here, but you can easily reduce this to on if you're using hash tables, for example. You could have an expected linear algorithm, or it's easier to do that in n log n time if you sort your edges with respect to their starting points, for example. Then you can have an n log n algorithm easily. But even having n square here, it doesn't matter. because the dominating part of the algorithm is steps 2 to 7, which will already take n cube time. So even if you have an n squared algorithm here, the overall running time complexity will be n cube. All right, so that's the slow convex solve. And then the books discusses how do we handle the degenerate cases. And here is this figure on the left is discussing how we are doing step 8, starting with arbitrary edge E1, how we add E2 to that. And the degenerate cases are really problematic for this. For example, if we have an edge which contains many points like this, all pairs of these points will be actually valid convexal edges, and we need to have a way. We need to change our if condition to test that. If something is on the line, in order to be a convexal edge, they have to be the vertices that are at the ends of this line. The other points should be contained in between them for them to be. So if there's some equality, for example, when we do the cross product, if the cross product turns out to be equal to 0, we need to check whether that point is in between this and that. If it's outside the line segment connecting this, then we are not going to add it to our edge set E. So the test becomes more complex in this degenerate case. All right, now I think it's a good time to have a 10-minute break. And after the break, I'm going to talk about the incremental solution, which is much more efficient. We will be able to solve this problem not in O(n) cube time, but in O(n) log n time, which is the optimal case. So we will have an optimal algorithm which will solve this convex solve problem. Then we will start our plane sweep technique in the second hour. Okay, any questions before we go into break? All right, no questions. So let's have a 15-minute break, and we will meet at 10:45. All right, I'm going to stop the recording, and I'm going to stop the meeting. I will see you all at 10:45. Stop sharing first. See you.